Welcome. In this video we're going to talk about reaction rate. Reaction rate is pretty much what it sounds like. It's how quickly a reaction happens. Now remember, a reaction occurs because reactant particles collide and they make product. So some reaction rates are naturally fast, like burning liquid hydrogen and liquid oxygen to fuel a rocket, and some are really slow, like concrete hardening or hydrogen peroxide decomposing. So sometimes we deliberately do things to speed up reactions, and other times we deliberately slow down reactions. Often we need a quantitative value or an actual number to express the reaction rate. So average reaction rate is defined as the change in concentration of a reactant or a product over time. And I've written this as a mathematical equation below. We use the delta or triangle to show change, and then concentration is shown with those brackets. So you can either measure the change in the concentration of one of your reactants or one of your products. But because that will give you different numbers or different rates, you have to indicate which reactant or product you were measuring. It will also give you different graphs because reactants are going to decrease over time because they're going to get converted to products. And products often start at 0 and then they increase in concentration as more and more product is made. So a couple more things to know about reaction rate and how to calculate them. It's expressed in moles per liter per second, and it's always given as a positive value. Even if your change is negative, like in the case of reactants decreasing, a rate is always a positive thing. You don't go a negative 30 miles per hour. The other thing is that the rate always starts quickly and then slows down over time because there's fewer reactant particles left to collide with each other. So just like microwave popcorn will pop really fast when it gets warm enough to start popping, but then it slows down as there's fewer and fewer reactant particles or kernels left to do the popping. And as I mentioned, the rate will be different for the different substances in the equation, and your molar ratios will help predict this. So you need to include the name of the substance that you were using to calculate your reaction rate. So I'm just going to scroll up here and show you a quick graph of how we often represent reaction rate. We usually express it with the time of the reaction, the time preceding for the reaction, and then the concentration of your reactant or your product. If it was a reactant, I would expect to see the rate going this direction, and if it was a product, I would expect to see the rate going this direction. And in both cases, you see that the graph is exponential, which shows me that the rate starts slowing down. The minute the reaction starts, the rate is getting slower and slower and slower and slower, which gives you this exponential curve. So here's an example of actually calculating it. Butyl chloride reacts with water and the following data is collected. Calculate the reaction rate of butyl chloride. And all I've given you is the concentration of the butyl chloride at 0 seconds and 4 seconds. I haven't included the balanced equation because we really don't need it to calculate the reaction rate. Instead, what I need for my rate is I need to look at the change in concentration. So I went from 0.220 to 0.100. And my change in time, I went from 0 to 4 seconds or 4 to 0. You can, if you want to, you can just take the big minus the little and then you'll have positive values. We're going to express it as a positive value anyway, so it really doesn't matter. But this difference would be 0.120 over 4 using my absolute values. So when I go ahead and divide this, then I'm going to come up with a rate of 0.03. And my unit is going to be, since this was capital M, that's moles per liter. And since my time was in seconds, it will be per second. So moles per liter per second. So here's another example. I've got Cl2 breaking down to form 2 chlorine ions. And now I've given you the concentration of my Cl2 at the beginning and after 3 minutes, as well as the chlorine ion. And it says, what is the average rate at which Cl2 is consumed? So if I scroll this up a little bit, my Cl2, well, I don't want to put Cl2 though, it's my rate. My rate in terms of Cl2, I go from a concentration of 1.2 to 0.600, and the time difference is 3 minutes. So then I've got 0.6 divided by 3. And when I go ahead and divide that, that is a rate of 0.200. Technically, I should hang on to my sig figs. I don't care if you do or not. But then this would be moles per liter, and this is per minute, since that's what my time was given in. Question number 2, what will the average rate for Cl minus be, and how much Cl minus should be produced after 3 minutes? Well, I really need to know how much is produced before I can find out what the rate for Cl minus will be, or at least I need to look at the balanced equation. So I can do this either way. I can either look at the fact that if the rate is 0.20 moles per liter per minute, and my balanced equation tells me I get 2 moles of chlorine ion for every mole of Cl2 consumed, I could just double this to get my rate. Or I could go ahead and take my 1.2 to my 0.6. Since I know I have 0.6 moles per liter that reacted, I could go ahead and double that and know that I have the 1.2. So either way you want to think of it, this should be, I should end up with 1.2 moles per liter of Cl minus produced. And as far as calculating my rate for the chlorine ion, that means I went from 0 to 1.20 in concentration, also in the 3-minute time. So this rate is 0.400 moles per liter per minute. Or as I said, we could have looked at the balanced equation and predicted that the rate of product being produced would be twice as much as the reactant being consumed, because that's the ratio indicated in the balanced equation, 2 to 1. So collision theory talks about why or how reactant gets converted to product. Atoms, ions, and molecules have to collide in order to react. So more collisions means a faster reaction rate. But most collisions actually do not produce the product, because besides colliding, a collision has to have enough energy, known as activation energy, and it has to hit with what we call the proper orientation, or hit in the correct spot. Kind of like when you're playing a sport like tennis or golf, when you hit what's called the sweet spot, you really have a nice successful hit for your tennis game or your golf game. So there's 3 requirements of a successful collision. First of all, they have to collide. No collision and no product can form. Secondly, they have to have an energy equal to or exceeding what's known as the activation energy, or enough energy to break the old bonds. And third, they have to have the proper orientation, so they have to hit, the molecules have to hit each other at the right place in order to break the old bonds and allow new bonds to form your product or new substance. So analogy I like to use is it's like throwing a dart at a dartboard. 3 things have to happen for your dart to stick. First of all, you have to throw the dart, and it has to hit the target. Second, the sharpened end of the dart must hit the target, because if it hits it sideways or backwards, it's not going to stick to the target. And third, the dart must have enough energy to actually pierce the target to allow it to stick. And this graphic is from your book, and it shows the different ways a carbon dioxide and nitrogen monoxide atom could be combining or attempting to combine. Actually, I guess it's carbon monoxide and nitrogen dioxide that are combining. But you can see that they hit up here with the 2 oxygen atoms hitting, and they simply rebound because that was the incorrect orientation. That's not where the bond needs to break. Here they collide and rebound because, again, the oxygen hitting the nitrogen atom still is not the correct orientation. But if we move down and look at the next one, now when the carbon hits the oxygen on the nitrogen dioxide, this is exactly where it needs to hit, and they form what's called the activated complex, allowing that activated complex to separate into our 2 new molecules. And finally, they could hit in the correct spot like they do in D, but still not form the product because they didn't have enough energy to actually form that activated complex.